Hello, I hope you're doing well. I'm going to talk today about epsilon delta proofs, and I'd like to start by introducing the concept of allowable error. And we usually use the letter epsilon to represent this allowable error. So this is true. I did build a workbench. This is terrible. This is my workbench in my garage that I built. Not much of a handyman. The board that I used was kind of bent right here, so I stacked another little board on top of it, and then the TV set on top of that. That way you can watch TV while the treadmill is out of frame. You can't see the treadmill. So yeah, if you want to go for a run. Yeah. So if you were building a workbench, then, and this is true when people frame houses, or, if you want to build a deck or something, and you're going to be cutting 2x4s, then the allowable error is 1/16 of an inch. So suppose that I had a board, and I was going to cut that board, and I'm going to try to cut it. Let's just say it's too long right now. And I'm going to try to cut it. Let's say that I wanted to cut it maybe so that it was something like, let's suppose that I wanted it to be like 36 inches. Okay. So, this is not NASA. I'm not going to shoot this workbench to the moon or anything. I just need something to hold up my TV so that when I go for a run, I can put the air compressor under there and stuff. So really, ideally, I would be able to make some measurement and then make some cut that was really perfect and great and made the board, exactly 36 inches. But we know in real life that that's not really possible. But it's not a big deal because, the floor of the garage isn't even really that even to begin with. The legs don't have to be perfect. So actually I have a little bit of wiggle room in there, maybe so long as I make the cut close to 36 inches, then I'll be good, right? So on this side, I could do 36 inches and maybe plus 1/16 of an inch. And then on the other side, maybe I would have 36 inches minus 1/16 of an inch. Okay, and so long as I put the saw, okay, now I've got to make a saw drawing. Right, this is how you draw a saw. Okay, so long as I put the saw somewhere in this range, then it'll be fine. The length of the board will be close enough to 36 inches that everything will be okay. So what this means is that I have some kind of range that I'm allowed to cut in. And so long as I make sure to put the saw within that interval, I know that the length of my board is going to be close enough to 36 inches. It may not be exactly 36 inches, but it's going to be within the allowable error. What your allowable error is depends on the context of the problem. If we want to think in terms of engineering, then imagine that I was using machine tools to create a gun barrel, and the measurements of the gun barrel were off by 1/16 of an inch. There is absolutely no way that firearm would function properly. It is 100% going to be dangerous, okay? I don't know, I tried to Google this, but I couldn't find the real numbers readily available. But like in my mind, if you're gonna machine tool something like a firearm, maybe your allowable error could be like 0.01 centimeters. Right? A very small allowable error. That way, really, the parts fit together perfectly every time. And in an even more extreme case, imagine that you were going to try to fire a rocket from the Earth to Mars, okay? Even if you're off by the tiniest little amount, by the time your rocket gets all the way to Mars, you're going to completely miss. So maybe in the context of something like NASA, the allowable error could be even smaller. What we want to do is encode the concept of a very good measurement, a very, very precise measurement, a kind of theoretically perfect measurement. And what do I mean by that? What I mean is that some kind of measurement that would work for any allowable error. Okay, a very, very good measurement. And we call that very good measurement a limit. So what do we mean when we say the limit of a function is a number L? What we mean is for any allowable error, it doesn't matter if you're building a workbench or if you're machine tooling a gun or if you're sending a rocket to Mars, our measurement is so good that it will work for any engineering problem that you can cook up. That's how perfect our measurement is. And what I need to do is, remember I had my saw that I had to make sure was in some range in order for the measurement to be good enough. So long as I choose my inputs within some interval, I need to be able to guarantee that the output is going to be within the allowable error. Now, just to clean this definition up a little bit and make it a little bit shorter, this interval of inputs around x naught, okay, I'm just going to call the radius of that interval, we call it delta. This is just kind of the Greek letter D for distance. And I'm just always putting these greater than zeros at the end of everything because I really want to communicate that these things are always positive numbers. I don't even know what it would mean for your error to be negative. I don't know how you could make a measurement that was the error was negative. I don't know. It's like more accurate than possible. That doesn't even make sense. So I'm just trying to make sure that at all times I'm reminding myself that that epsilon and delta always represent positive amounts. Also, this definition, I've written down the definition as though it looks like it's a function of a single variable. But if you're in multivariable calculus, then you can just absolutely allow these objects to be vectors. And then all the definition just copies the same. So let's see if we can take this general concept and just kind of turn it into something that's a little bit more robust, a little bit more mathematical. I've just taken our concept that we're trying to encode and just kind of put that in a little bit more mathematical language. So let me try to just unpack this and break it down a little bit. So our measurement is supposed to work for any allowable error. So that's what I've got right here, for any allowable error. Our measurement needs to work. And what the power that I have in order to make this measurement work is I can always require that my saw is within some interval. So that's what this part right here is trying to communicate. So long as I put my saw in the right place, so long as I am close to the correct input value, I can guarantee that the function will be close to the limit. And what do I mean by close? What I mean is the distance between them is less than the allowable error. I missed a little vector symbol right there. That can be a vector. Okay, so I can actually write this in an even shorter way. So I'm just going to try to make this definition just a little bit more compact here. So it starts off pretty much the same. For any allowable error, I'm always going to generate some interval of inputs that will keep my measurement within the allowable error. And it's our culture for this right here, this D. All I'm trying to say here is the distance between x and x naught. So this is just our cultural notation for the distance between them. And this right here, this is our mathematical way of saying if then. Okay, so that's part of the original definition, right? The way it works is if my inputs are in the good range, then my function will be very close to the correct measurement. It will be within the allowable error of the correct measurement. So so long as x is close to x naught, we can guarantee that f of x will be close to L, and we can still allow for these things to be vectors. Yeah. So this definition is nice because it's independent of the dimension that you're talking about. I've just phrased things in terms of distance. But just to be clear, if this is a Calc 1 problem, when I say the distance between 2 points, the input is one-dimensional, so I'm just talking about the distance on a line. So that's just the absolute value. And then, I also want to do an example where the domain is a two-dimensional object. So here I put the definition of distance in 2 dimensions. And then the context of this lesson is going to be where the outputs are scalar functions of multiple variables. So in this case, then the output is just a single scalar. It's a number. So the distance between the function and the limit is just going to be the one-dimensional distance. So just the absolute value of the difference. I can actually make this even more compact. I'm going to show you the kind of fancy math notation for how you can really write this like in our little math secret code language thing. This is the definition that you'll see written in a lot of Introduction to Real Analysis textbooks. So just to clue you in, the upside down A means for all. And the backwards E means there exists, and a comma means such that. Also, you'll sometimes see it written with a colon like that. So if I read this, for any epsilon, there exists a delta such that if the distance between x and x naught is less than delta, then the distance between f of x and L will be less than epsilon. Okay, that's a lot of really dense theory. Let's see if we can jump in and do some examples from Calc 1 and some examples from Calc 3 to try to calculate some specific deltas given a specific epsilon and see if we can do like a full legit proof that the limit of a function is something else. Okay, so I've given us a function, 3x plus 2, and I've given us an epsilon, 0.1, so our allowable error here is 1/10. And then just to be clear, in this problem, 0 is the x naught and 2 is the L. So basically, this is like a step on the way to learning how to prove that the limit as x approaches 0 of 3x plus 2 is equal to 2. Okay. Yeah, so let's just do this calculation. Given an epsilon, what is the delta? So what I would really like to do is to trap the function in some kind of range. Some kind of range where I make sure that this graph stays very close to f of x equals 2. If right here is y equals 2, then I'm allowed to go up by 0.01, so I'm allowed to go up to 2.1, and I'm allowed to go down to 1.9, and I will still be within the allowable error. So that's what I set up here. This is f of x minus L. So what I want is the distance between the function and the limit to be less than the allowable error. Okay, so let's just start doing some math. Yeah, the 2's cancel, so this is when the absolute value of 3x is less than 0.1. And just to clear the absolute values here, what I need to require is that 3x is in between 0.1 and a negative 0.1. So now I can divide both sides by 3. So negative 0.1 divided by 3 is less than x is less than 0.1 divided by 3. So that's it. What this means is I need to pick x's that are very close to 0, that they are so close to 0 that they are less than 0.1 divided by 3. And if that happens, you can see because the slope of this line is 3, then what I'm going to need to do is come in and make sure that my x's go in that range. If I were to do a line where the slope was less steep, like this, then for a similar epsilon, right, I would actually get an even wider range of x's. Now I'm allowed to pick x's that are anywhere in this range. If you pick a very steep line, then for an epsilon, you're going to really require a very, very small delta. Okay, so in this problem, delta was 0.1 divided by 3. And I know so long as I pick, so here's 0, and I can go to the right by 0.1 divided by 3, or I could go to the left by 0.1 divided by 3. So long as I stay in that little range right there, then I will guarantee that the height of the function will be within 0.1 units, centimeters or meters or whatever, of the limit there too. Okay, let's repeat this and turn it into a legit proof here. So now, instead of giving you a specific epsilon, I'm going to give you a general epsilon. So now we're really employing the concept behind the limit. Now, instead of saying do it for this one specific epsilon, make it work in this one context, maybe, 0.1, I don't know, maybe that was, maybe that was building a computer or building a car or something. Now, make this work for any epsilon. So no matter, we're going to leave like epsilon like a variable. So no matter what epsilon they give you, we're always going to come up with a delta. The way that we solve these problems is backwards than the way that we answer these problems. The logic behind this process is you are given an epsilon and you are asked to produce a delta. So in order for your solution to follow the reasoning in the definition, you start with the epsilon and you begin by producing the delta and then go on to show that that delta is going to work. You're given an epsilon greater than 0 and you immediately produce a delta. So I'm going to choose delta equals epsilon divided by 3. Okay, then assume the distance between x and 0 is less than delta. The distance between x and 0 is just the absolute value of x. And delta, I chose that to be epsilon divided by 3. I realize now 3 is a bad choice of numbers. Look at this crazy symbol, epsilon divided by 3. I don't know why people are confused about this. What's wrong with those symbols? Anyways, I already picked it, so let's keep going. Okay, so then now I'm going to multiply both sides by 3. So then 3 times the absolute value of x is less than epsilon. So then 3 is positive, so I can move it inside the absolute value symbol. So the absolute value of 3x. Now inside the epsilon, this is my goal here. That's where I'm trying to get to. So what I'm going to do is just add and subtract 2. Okay. And I end up with exactly the statement that I am trying to arrive at. So one more time here, the logic is you start with an epsilon, then you choose the delta that you want, and based on the assumption that the distance between x and x naught is less than delta, you arrive at the conclusion that the distance between f of x and L is less than epsilon. So the logic really does need to flow in that order. Give an epsilon, provide the delta, make your conclusion. Okay, so I messed this up last time I tried because I rounded in the wrong direction. So let me work this one out again and see if I can come up with a smarter delta, maybe a delta that actually works. Okay, so I've given us a function. This time it's a nonlinear function, f of x equals x squared. I give us an epsilon. It's a pretty small epsilon there, 0.01. And x is going to 3, and the limit is going to be 9. So let's see if we can calculate a delta that's going to work here. Here's what we want to happen. This is the goal. So this happens when x is between 0.01 and negative 0.01. The goal is to get the absolute value of x minus 3 is less than delta, and then we're going to work backwards. So I'm trying to turn this into x minus 3. Okay, so I'll add 9 to both sides. Okay, now let me square root everything. Okay, this is possible because the square root is a strictly increasing function, so I can always apply it to both sides of an inequality. And remember, the goal is to try to get x minus 3. So I'll subtract 3 from both sides. So I guess subtract 3 from all 3 sides is a compound inequality. And given an epsilon is 0.01, I'm just trying to figure out a delta that is going to guarantee that this process is reversible. So I know that all of the x's that are in this range are going to guarantee that x squared minus 9 in absolute value is less than 0.01. So I just used the calculator to approximate these two values. And then what I can do is just not quite go out that far, right? And just so if I just make sure that I stay inside these boundaries, then I will guarantee that the difference between x squared and 9 is less than 0.1. So what can I do here? So this one, if instead of going to the left 0.001667, you know, maybe I can just not quite go out that far. Maybe if I just go out to 0.0016, and that's negative because I'm going to the left there. And then how far to the right can I go? Say 0.0016. Okay, now that is guaranteed to be inside the square root of 9.01 minus 3, because whatever the true value of this decimal is, it has more digits. So if I just drop those digits, I'm always guaranteed to not go out that far. So here I'm going to choose delta equals 0.0016. And then what I will have is the square root of 8.99 minus 3 is always less than negative 0.0016 is less than x minus 3, which is less than positive 0.0016, which is less than the square root of 9.01 minus 3. So I can always just, you know, I mean, I'm free to choose delta as small as I want, right? I mean, if I wanted to, I could choose delta to be 0.00000001 if I wanted to. You can make delta as small as you want. The logic is just find a delta that will work. So I've done it. This happens when the absolute value of x minus 3 is less than 0.0016. Okay. All right, so that's it. We did it. Given this specific epsilon, we were able to find a delta, but when we did it with linear functions, it was really obvious, right? Right, if you had like y equals 3x or something, then it was easy. You could just choose delta equals epsilon over 3. But this time, my solution required on some like clever observation and clever rounding. So I'm going to leave you to think about this. How could I turn this into a kind of proof, right? How could I do this in a way that didn't require any kind of rounding? Well, one thing that you know, what we're trying to do is to make x squared minus 9 go to 0, right? So really what we're trying to do, I can factor this and look at x plus 3 times x minus 3. I'm trying to make this go to 0 as x goes to 3, right? So when you look at this expression, really the reason that this polynomial is going to 0 is because as x goes to 3, this one is going to get closer and closer to 6, and this one is going to get closer and closer to 0. So the whole thing is going to essentially kind of 6 times 0. So the hint here is to factor. When you're trying to prove this, if you want to write this up as a proof, then you're going to kind of have to look at the reason why it's true. And the reason that it's true is because it factors and one of the terms going to 0. So if you want to try to write up a proof in general, given a general epsilon, find delta, then feel free to send it to me and I'll check and see if the details are correct. Okay, so here I've come up with a linear function. Whoops, I didn't do a very good job with my notation. You want to really be clean with your notation, make sure that everything matches. And we're trying to be precise here. So I've given us a function and a point of interest, right? We're trying to take the limit as xy goes to 0, 0, and this limit is going to be 0. So let's find delta. So what we want here is the distance between f of x, y, and 0 to be less than epsilon. So the output of this function is just a single variable, z, we usually think of it here, but it's just a number. So that means this distance formula is a one-dimensional object. Okay. And I guess technically the distance between the function and 0, I want this to be less than epsilon, okay? But this is silly. I don't need to write minus 0 there. So I want this to be less than epsilon. Okay, so the goal here is to make the distance between f of x and L less than epsilon. So let me start working with these. So the absolute value of f of x, right, if these things, if they're positive numbers, if they're both positive, then the absolute value doesn't do anything. And if one of them is negative, then their difference is just going to get smaller. And if they're both negative, then the absolute value just turns the whole thing negative. So basically what that means is the biggest that this thing could be is if both of the objects were positive. This is a really interesting trick. And I encourage you to try to think about this trick that I've done here and justify it to yourself. It has a name. It's called the triangle inequality. And it's a big part of introductory math theory. So if you want to do some reading on this inequality, I encourage you to look up the triangle inequality. Anyway, so now I can factor out the 3 and the 5. Okay, and let's look what's going on here. So we're in the xy plane, and the goal here is to find some distance so that the distance between x and y and 0, 0, the distance between those 2 points is less than delta. So if you have some circle, that's what this is the equation of. This is the equation of a circle, right? This distance in 2 dimensions, oh, that was a good circle, is going to be the square root of x, well, x minus 0. So this will just be the square root of x squared plus y squared is less than delta. So that means that this is a circle and the radius of this circle is delta. So that means the absolute largest that x can be is this point right here, and the most negative that it can be is this point over here. So this means that x can be at most delta, and y can be at most delta. So what I want to require is that 8 delta is less than epsilon. So I'm going to choose, oh, and we know what that is this time. Epsilon is 0.1. So what I want is 8 delta to be less than 0.1. So this time I will choose delta to equal 0.1 divided by 8. Okay, that's interesting. So long as I guarantee that x and y are in a circle of radius 0.1 divided by 8, I can guarantee that the distance between f of x and 0 is less than 0.1. So I want to challenge you now to try to work out some of these problems where the function is a nonlinear function. Maybe you could try some quadratic functions and some specific deltas and see if you can do kind of the rounding trick. And if you really want to, try to see if you can cook up some real formal proofs of maybe some limits for linear functions like these ones, or maybe some quadratic functions. I'm always happy to get these proofs. If you want to send me your proof, it would just be a delight for me to go through and read it and see if it holds water. Have a good day.